Okay, and we're back. So, we are going to finish up talking about electrical power, do a little bit more work with some of the equations, and then we'll make some calculations. We'll see some interesting results about the brightness of certain light bulbs. Number 3, if the resistance of a constant voltage circuit increases, what happens to the power developed by the circuit? Okay, so we're saying in there's some very important words that people tend to skip over. Constant voltage circuit, meaning the voltage from the battery, the voltage supplied to the circuit will not change. And if we increase the resistance of that circuit, or part of that circuit, what happens to the power developed by that circuit? There are a couple different ways you can think of it. Let me show you the way that I have written down, then I'll show you an alternate way. First way to think of this is to think of Ohm's law. Remember, Ohm's law says V equals IR. So it says the resistance increases. So if R increases, we want to say what happens to the current. Now some of you might be tempted to just go right ahead and say that the current decreases, and that's right, but that's only right if you know one other thing. That is only right since we acknowledge that the voltage is constant. If you're just told how one of these changes and you're not told that that one of the others stays the same or also changes somehow, if you're not told information about two of the variables, you can't predict what happens to the third one. So the fact that it says constant voltage is very important. Since it says if R increases and the voltage, this is my symbol for stays the same, then you can conclude that I decreases. If you weren't told that the voltage was the same, or you couldn't reasonably infer that, you couldn't make that conclusion. But we were told that, so we can say that. So the current goes down. We also know that power is equal to, in this case, V times I. We already know that V does not change, and we just found out that I decreases, so the power must decrease as well. And that's a type of reasoning that you can use for some questions in this class. You use them for a lot of questions in AP. Okay, there's a lot of questions that ask things that are sort of like that, and you even have to start justifying and writing about them. The other way that you could determine that, if you want to know the power that gets developed by the circuit, I think there are some other ways you could do that. You could look at some of the other power equations. Notably, you could probably just look at the P equals V squared over R equation. You're told the voltage is constant, but the resistance increases. Since P equals V squared over R, if this stays the same and this goes up, the power has to go down, which is the exact conclusion we have here. I like rationalizing in terms of Ohm's law and then power, but if you want to go that one step, you can do that as well. Okay? All right, let's get into some examples, more with numbers. Number 4, a person has 2 light bulbs. First light bulb is 20 watts, while the second light bulb is 40 watts. That's describing the power of these light bulbs. The person first creates 2 simple series circuits, each consisting of a 10-volt battery and one of the light bulbs. So you have 2 separate circuits going on. So I have 2 different things that are happening. Compare the currents in each circuit. So each circuit is just a battery, wires, and one of the light bulbs. We want to know the currents in each circuit. Well, we're not told the resistance of the light bulb. Matter of fact, we find that in B, but we do know the power for each light bulb, and we know the voltage drop. Since we're told the voltage, since we're told the voltage gain for the battery, and it's a simple series circuit, only one thing in it, we know the voltage drop of the light bulb for the light bulb should be the same thing. So, since we know the power and the voltage, we can use P equals VI to find the current. So this is for, let's say, the 20-watt light bulb. So 20 watts equals a 10-volt drop. How much current would have to be going through this light bulb that has a 10-volt drop associated with it to make the power be 20 watts? As you can see from this equation, there must be a current of 2 amps for the 20-watt bulb. We can do the exact same thing for the 40-watt bulb. Just change the numbers around. 40 watts, 10-volt drop. How big is the current? I must be 4 amps for the 40-watt bulb. And now based on that, or even just based on my original numbers, I can find the resistance for each light bulb. I'm going to choose to use Ohm's law because that's, probably the one you're most familiar with. But there are other ways to do this. We know it's a 10-volt drop with 0.2 amps. Or no, excuse me, not 0.2 amps, 2 amps times R. That would be a resistance of 5 ohms. And I'm going to put R20 to show that that's for the 20 watt light bulb. V equals IR over here. 10V equals 4 amps. We're looking for R. R is, and this is R40, 2.5 ohms. Okay, I guess we don't need this. Which light bulb is brightest? And explain your answer. Brightness directly correlates with power. The more powerful something is for a light bulb, the brighter it is. So this is actually a very easy question. The brighter light bulb is the one that has a higher power rating. So, in this case, it is the 40 watt bulb. Okay? And I can show this to you on the simulation. I'll take you over to see that. I have these two circuits set up. Remember, we found out that one of the light bulbs was had a resistance of 5 ohms, the other had a resistance of 2.5 ohms, and we have them hooked up in basic series circuits to 10-volt batteries. I'm just going to attach the ammeter here so you guys can see that the current is in fact 2 for this one, and that the current is in fact 4 for this one. And the way that this simulation shows the brightness is by the number of lines and how big they are. And you can see that they're both pretty bright, but in this case, we see that the one on the right, the lower resistance one, which again, the lower resistance one was the one that had a power rating of 40 watts. That one does seem brighter. There's more lines and they're bigger. Okay, so, and that's just to simulate brightness. So brighter light bulb is the one that is more powerful. Okay, let's do the last one. Okay, move this up. All right. Two different light bulbs with known resistances are connected in parallel with a 15-volt battery. The resistance of the first bulb is 60 ohms, while the resistance of, well, the second bulb's resistance is 150 ohms. I'm just going to sketch this off to the side here. So I've got a battery, and it's a 15-volt battery, and that 15-volt battery, let's see, is connected in parallel to two light bulbs. There we go. Okay, this is 150 ohms, this is 60 ohms. First thing, what's the equivalent resistance of this circuit? Well, light bulbs are just basically resistors that also give off light. Okay, so we can find the resistance of something in parallel by using the 1 over Req equation. In this case, 1 over Req equals 1 over R1 plus 1 over R2, which would be 1 over 60 ohms plus 1 over 150 ohms. I'm going to do that on the calculator. 1 divided by 60 plus 1 divided by 150, and I get 0.023333. Remember, that's not my answer. I need to take the inverse of that. I get that Req is approximately 42.86 ohms. That's Req. B asks me what is the total current in this circuit and how much current goes through each of the light bulbs. So I'm finding three different things: the total current and the current through each branch. Remember, when we get to a branch, the current in the branches must be lower than the current coming out of the battery because charges cannot simply be created or destroyed. There's a conservation of charge rule going on here. Okay, so I'm going to do VT for total voltage equals I times Req. This will be the current coming out of the, this will be the total overall current. We know the total voltage gain in the circuit is 15 volts. I, 42.86 ohms. We solve for I. So let's see. Divide that by 15 and take the inverse. I get 0.35 amps. Okay? You can double check that math if you want to. That's the total current. What if I want the current in the 60 ohm resistor? So I'm just going to put 60s here. Since it's a parallel circuit, the voltage drop over everything, the voltage drop for each individual resistor, or in this case lamp, is the same as the voltage gain from the battery. So in this case, that would be 15 volts. I is what we're looking for, times 60 ohms. 15 divided by 60 is 1/4. So the current through the 60 ohm resistor is 0.25 amps. Now, there's multiple ways you can get this next one, and it's not a bad idea to do both as a way to double check. V150 must equal the voltage drop for the 150 ohm resistor must equal the current through the 150 ohm resistor times the 150 ohm resistor. Again, the voltage drop is going to be 15 volts because in parallel, each resistor, in a very basic parallel circuit like this, each resistor has the same voltage drop as the voltage gain of the battery. I is what we're looking for, times 150 ohms. 15 divided by 150 is 1/10. The current through the 150 ohm resistor is 0.1 amps. And just to double check, if we add up those two currents, they should equal the current coming out of the battery. 0.25 plus 0.1 is 0.35. Exactly what we got there. Now, we just simply ask which bulb has the most power and is therefore the brightest. Are we talking 60 or are we talking 150? So this is going to be the 60 ohm side. This is going to be the 150 ohm side. I know the voltage drop and I know the current, so I can use those two to find the power. 15 volts times 0.25 amps. 15 times 0.25 is 3.75 watts. Same equation over here. 15 volt drop. The current is 0.1 amps, I suppose. There is a 1.5 watt power for this bulb. So, which bulb has the most power and is therefore the brightest? That would be the 60 ohm light bulb. And the reason that ended up happening is because the resistance of that bulb was less, that branch of the current of the circuit was able to draw more current. And since it could draw more current, it had a greater power. Okay? I'll show you this real quick. Here's the circuit. The only thing that's a little different about this circuit is you can see the 60 ohm branch is fine. Light bulb. I couldn't get all the way up to 150 ohms, so I just did two separate 75 ohm light bulbs. The effect is exactly the same. Okay. When I connect this, you'll see that the circuit starts. We have a current of 0.35 amps coming out of the battery. We have a current of 0.25 amps coming out of the 60 ohm light bulb and 0.1 amp in that other branch. And if you look, you can tell that the 60 ohm light bulb is much, much brighter in this case than the other two light bulbs. Even combined, there's barely any light coming off of them. Okay? Everything works out just like we said. Last question, just to follow up. One of the reasons we do this is we want to know how much energy we are spending. If the brighter bulb shined for 4 minutes, how much energy would it dissipate? Remember, power is simply the amount of energy transferred or work done divided by time. So therefore, the energy, if we want to find the work done or how much energy is transferred or dissipated, we simply rearrange the equation. The work done or energy transferred equals the power multiplied by the time. Only thing you gotta be careful of is 4 minutes. We gotta convert that to seconds, okay? And the reason we have to convert that to seconds is because a watt, which is 3.75 watts, that's the power from up here, a watt is a joule per second. We can't mix minutes in with that. So we do need to figure out how many seconds are in 4 minutes. 4 times 60 is 240 seconds times 3.75. The energy transferred is 900 joules. Okay, there's a little bit about power. The calculations are pretty straightforward. If you have any questions, feel free to ask. Have a nice day.